Welcome to Tarragona from CellSpex. Today I'm going to give you a whistle-stop tour of Tarragona. Like Microsoft Word or Excel, Tarragona is document-based, so first I need to open a document. And when I open the document, it reappears exactly the way I left it. This document has 4 tabs, and in this tab I have 6 graphs. When I click on the graphs get a pink box around them to show the graph is selected. When I click on the trace in the graph, it goes pink to show it's selected, and if I double click on it, I can edit its properties. So I'll make this thicker. Tarragona has full support for Greek characters and mathematical symbols, so I can change this U very easily to a mu for micro. In this graph, I have 2 traces, a green one and a red one. If I select this one by clicking on it and then shift select this one, they're both selected. I now double click and I can edit both together. Because they have different colours, the colour box is empty. If I change the colour, I'll change the colour on both. If I change the line width, I'll change the line width for both, but I won't change the colours. So I can also cut and copy traces between graphs and between documents. I select this one, edit copy, I select this graph, edit paste. I can multi-shift click to copy 2 at a time, copy and paste. So I clear that and I can then copy multiple parts together. Copy and paste. If I double click on the axes, I can change the axes. So now I've changed it to minutes, or I can double click on it and set a start and a stop. And then I can hit the rescale button to rescale. A Tarragona document also contains study data. If I go into spectra contents, I can look at the spectra in the study. So this is one block of spectra called cytochromes. Each spectrum in the block has 1022 wavelengths, and there are 573 spectra, one for each time point. To look at my temporal data, I go into data contents. So these are my temporal data components. So time, oxygen concentration, oxygen consumption, and these are components of the spectra. So you can consider these as columns in a spreadsheet, and each row in the spreadsheet is one time point. So the time column will contain the time for each time point, and this will contain the oxygen concentration for each time point. And then the spectra are also like a column, but each cell in the column now holds a complete spectrum instead of just a single data point. So if I want to view my spectra, I select a graph, I go to Spectra, View, and then I choose how I want to display it. So I'm going to put wavelength on the x-axis and intensity on the y-axis. So that's the spectrum I was collecting. Then if I want to view my temporal data, I'll put it into this graph. So I select the graph, go Data, View. I choose what to go on my x-axis. I'll put time, and what to go on my y-axis, oxygen consumption, and I add it to the list of plots. And then I can make multiple selections for this graph. Click OK, and there it appears. Likewise, I'll remove that. I can Data, View, and I can view oxygen concentration on the x-axis, oxygen consumption on the y-axis. I either add or double click to get it into the list of plots. And now this is now oxygen concentration against oxygen consumption. So because my data is tied together, I can animate my data. So if I select this graph, go Graph, Animate, I now put a cursor on, and when I move the cursor along the temporal data, you see that the spectra changes for each data point. So here, for this data point, the spectra looks like this. For this experiment, I had some mammalian cells sealed in a little chamber, and I was measuring the oxygen concentration against time as I gave them a number of different drugs, as indicated by these events. Although I was measuring the oxygen concentration, I really wanted to know the cell's oxygen consumption. So the cells are sealed in a little chamber, and as they consume the oxygen concentration goes down. So the rate it goes down, the gradient, is the oxygen consumption. To create the oxygen consumption from the oxygen concentration, I set up an operation. So in Contents, Maths, I created an operation with the Create button called oxygen consumption, and I sent the output to the oxygen consumption temporal item. The operation I used was a derivative, and then the source A was oxygen concentration and source B was time. There are several different operations I can do, A plus B, A minus B, etc. But I chose the differential with the Lorentz algorithm, and these are the parameters I chose for it, looking the help for all of that. And then I had to multiply the output by -1, because as the cells consume the oxygen goes down for positive oxygen consumption. So I click that, and that gave me a continuous online trace of the oxygen consumption as I was doing my experiment. So I'll now show you the fitting. So the spectra I'm collecting are made up of 5 different spectral components which are all varying independently. So I have my fitting model set up, and this is a linear combination of model spectra, and so these are my 5 spectral components, my model spectra. If I look at this one, you can see the spectrum I'm using, and this has a peak at 550 nanometers, so this spectrum is giving rise to this component here. So I'll now show you all the components. So if I shift select and copy to the clipboard, I can now make another column of graphs. I'll just select all these graphs and then merge them together, and then paste in the spectra into here. And because I have very small changes in concentration of each component, they're actually in OD per nanomole per centimeter, so I'll change that to the standard unit, OD per millimole per centimeter. And you can now see how big they are. But they're all, as you can see, they're all overlapping. So what I'll do is I'll select all of them and then I'll tier them. So I'll step size of 25, and so they'll now be tiered up. So now you can see all my spectra. So this is the peak at 550, given this peak here. These 3 are given the shoulder here, and this peak is given my peak at 605. So the way this fitting model works is it takes each spectral component, multiplies by the concentration change of that component, adds that together to give the fit to the data. So I can show you that here. So if I go fitting, view, I look at the data, the fit, and the residual. And I should make the fit slightly thicker so it's easier to see. So the black trace is the data and the thick blue trace is the fit to the data. So the way the algorithm works is it varies the concentration of each component so that the scaled component, when added together to give the fit, gives the best fit to the data. And as you can see, my fit is going through the data. The residuals are the difference between the data and the fit, and the residuals are flat around 0, so I have a very good fit to my data. So once it has the best fit, it will take the concentration of each component needed to form that fit and output it to the data items, and then these are then plotted here. And I can show you how those scaled spectra look. So if I go view, I look at the data, and these are the scaled components of the fit. And so you can see for this spectrum, the red spectrum is shown by my 550, these 3 are the scaled here, given the shoulder, and the green one is given my peak at 605. So just to recap, for every data point I have a spectrum. I fit the spectrum with these 5 components, and that tells me how much concentration of each component there is in my spectrum, and then I plot that out into the data. And that all happens in real time and online. So this is what Tarragona looks like when you're actually collecting data. So I've just added a dose of FCCP, and that's called a spectral change because this signal has gone down, and it will also increase my oxygen consumption. Now you can see your oxygen consumption go up. And as you can see, you can watch everything play out as it happens. I'm just going to add another dose of FCCP. There, it went in there. I'll add an event to show where that went in. So that was FCCP, 100 nanomolar, and I'll set that as my default text. So that went in there. You can see there was another change in the spectral components. So this went down. The oxygen consumption is coming down again. And now I'll add another dose of FCCP. And that went in there. So I'll put my event on. It went in there. And I'll use the default text. So you really can see your whole experiment unfurl before you as you do it. So there are other things. I can now pause my update. So I'm still collecting data, but now I can look at what's happening to my data, and then I can unpause it and it will go back to where I was. I can show everything up to now with this button, so it's paused. This is my whole experiment up to this point, and then unpause it. At the moment I'm displaying 2 minutes back in time when it's scrolling. I can change that to 1 minute back in time or 3 minutes. And so now my cells are running out of oxygen. You see these big spectral changes which are being followed in the fitting, and then you'll see the oxygen consumption come down to 0 as well because it can no longer consume oxygen. So now my experiment's finished, I'll show you a little bit of data analysis. So if I put a cursor on and move it to this point, you can see there's very small changes in my signal. So if I zoom this up by drawing out a rectangle, you see there's a small change, but you can't really see it in the data in the black line because there's too much noise. So what I'll do is I'll average my spectra over this epoch. So I put 2 cursors on, I choose the epoch I want to average over, and then go spectra average. And I'm going to average the change in attenuation. So the red line is my average and the black line is one of my spectra. And I'm averaging between spectra 128 and 187, and the black one is currently at spectra 128. So as I change this, I change my black one. So I'll take that spectra, I'll copy it to the clipboard, I'll then paste it into here. And now you can see that there's a small loss in the 550, so that's gone down, and there's an increase in this blue one, which has gone up. So if I take that spectrum, fit in and select it for fitting, and then fit to that one, you can now see how my fit is fitting through the data. So I can use this to confirm that these small changes are real. So one of the things I'd like to know is what my baseline oxygen consumption is, and then what the oxygen consumption is after every drug that I've added. And so I'll show you how to pull that out of the data. So I'll open a new tab, and I'll split this graph into 4, and then I'll shift select these and merge them together. And in this one I will view my oxygen consumption, and then I'll show my events, so view my events. This one I will turn into a worksheet, and then in here I'll put 2 cursors on, and these are mean and standard deviation cursors. So what this is showing is the mean value between the 2 cursors and the standard deviation between the cursors. I'll select my first column, select the trace, and I press the insert key, and that will place the cursor value into the column of the worksheet. I'll then move to the next part, insert those with the insert key, press the insert key, press the insert key. Okay, for this I should have given it more time to form a baseline, and then that's after my last one. There. So now I have a list of the oxygen consumption at each time point. Notice in my cells I have both the mean and standard deviation value. This is different from Excel. I don't need the standard deviation, so I'll remove those. So worksheet, mean and standard deviations, remove. So now I'd like to plot these out as a bar graph. Before I do that, I just need to do a little bit of a manipulation. So I'm inserting rows, and then I'm going to name these workshop column row titles. So I'm going to name this row my study name, so it's 2019 0228, date it was collected. Next, this is baseline, oligamycin, and then that was 100 nanomolar of FCCP, and these were going in addition. So after 2 doses I have 200 nanomolar, 300 nanomolar, 400 nanomolar, and 500 nanomolar. And then in my last one I create a column break. So I can now select this column, shift click to this graph, go worksheet, create a bar plot. And what it's done at the moment is it's averaged all of these values together. That's not the way I want it, so I'll double click, go into its contents. These are my data, and I want to plot it out in contiguous mode. So now it looks like this. So now this is my oxygen consumption baseline, oligamycin, and after different concentrations of FCCP. So now I want to merge this with my previous data, so I'm going to select it, copy it to the clipboard, go to this figure, and here is my other data. So I have 3 sets of data in here from the 25th, 26th and 27th. And I may want, for instance, to look at the statistical difference between these 2 bars. So I select it, add on the test. It's between 400 and 500. It's a t-test, and that gives me a p-value of 0.094. Double click on this, and I'll paste in my new data. In goes my new data, and I've now got a significant difference. Finally, I would like to plot this out as a figure. So I select the graph, copy it to the clipboard, I go to print preview with this button. I have my page set up, it's 90mm by 90mm because that's what my journal size is. So I'd paste my data in, fit it. So this I can make as a star because it's significant. I want my labels to be at 90 degrees so I can see them clearly. I don't need that. I can now insert text to show that was FCCP, and I want to change this to just VO2 for oxygen consumption. And now I have a figure, and then I can just go File, export that figure to a TIFF file and upload it to my journal. Thank you very much.